In this video, I'd like to finish up our review examples for this week, and in doing so, we're going to cover some 2D kinematic equations. Now, it's possible that this is the first time you've seen some of these equations, but I really wish that it isn't the first time. Please remember that I do have a series of videos that are linked and playlists that are linked in our Schoology page. You really should be watching these ahead of time before we get to see each other in class. This link here takes you to an instructor who talks about all of Chapter 3 and points out some interesting information about the formulas there. And then this playlist shows several examples of problems from the back of the textbook in Chapter 3. So in this example, we've got a ball that's thrown horizontally, and we'll assume that it's perfectly horizontal right from the top edge of a 120 meter tall building, and it lands 185 meters from the base of the building. So I definitely think we should report our given information. This time, however, we'll probably do so with a bit of a diagram. So clearly this diagram isn't drawn to scale, but hopefully it gives you an idea of what's happening here. We've got a building that's 120 meters tall, so the ball, as it travels in this pathway, is going to change in the y direction of 120 meters. The x direction is 185 meters. That's the distance that it'll actually travel. Now, as a point of clarity, the building is 120 meters tall, but I'm going to mark this as a negative 120 because the ball itself is actually falling downward 120 meters. And we should also note that the acceleration in the y direction is always going to be negative 9.81 meters per second here on Earth. So in question A, we need to know the time value because question A is asking how much time passes before the ball strikes the ground. Now we will again use the same formula sheet that we had before, and the tough part about 2D kinematics is that the motion in the x direction and y direction are essentially separate from one another. And when we're computing the time that it takes for this object to fall, since that's a vertical movement, we really only need to focus on this group of potential equations. The horizontal trajectory in this case has no effect on the amount of time that this object is in air. And we've got some examples that we can show to illustrate that, but just take my word for it for this math here today. The motion in the y direction is all that we need to worry about. And since I know the initial velocity in the y direction, I didn't write it down, but that's 0. And I know the acceleration and the delta y. I think this is the equation that we'll use this time. So on these formulas, I will be a little bit more deliberate and use the subscript y to indicate that we're talking about velocity in the y direction or acceleration in the y direction. And again, this object had no vertical velocity as it was released or as it came off of the building. So that's why I'm assuming, or we can safely assume, that the initial velocity in the y direction was 0. So after substituting known components into the equation and a fair bit of algebra in order to isolate the t values, it's worth noting that this does disappear. So I multiplied by 2 on both sides of the equation, divided by negative 9.81, that left me with t squared, and the radical around t squared gave me the end result. The units in this result are going to be meters divided by meters, which cancel, and we're left with seconds squared when we divide by the denominator, or divide with a fraction whose denominator is seconds squared, then that unit becomes seconds squared, and the square root of that will be seconds. So this gives me a unit of seconds, which is good. That's exactly what we're after. And the math off the calculator comes out to be 4.95 and some change. Our least accurate measurement contained 3 significant figures, so we'll use 3 significant figures in this result. Part B. So question B, we need to know what the velocity in the x direction was initially, so v naught x for the horizontal component. And again, based on what we have, or what's been given, or what we've now calculated, we've got to find the appropriate equation for that. And this one looks pretty good to me. We know our change in x. We now know the time that the object's been in the air, and we also know the horizontal acceleration of the object. Now this one's, again, relying on some implied values. but it is important to note our horizontal acceleration is actually 0. And the reason why I'm going to say that this is 0 is as follows. There was no mention of it in this problem, but we often say this from time to time where there's no effect of wind resistance. The wind is going to be ignored for this particular example, or air resistance for that matter. And after a ball is thrown and released from the person's hand, there are no more forces being imparted horizontally on this object, either pushing it forward or essentially pushing it backward due to resistance. We're ignoring this one. And after that ball's let go, there's no more force being applied to that ball moving forward. So at that moment of release, acceleration, or the change in velocity, does become 0. So the change in velocity is 0. There is some velocity, but there's not going to be any change in velocity in this situation. And again, that's pretty tough to internalize if this is the first time you've really thought about a problem like this. But it is indeed true, so let's just get used to that, and we'll try to explain it further next time we see each other. And because that large component reduces to 0, then the math becomes pretty straightforward here. The initial velocity in our x direction is equal to 185 meters divided by 4.95 seconds. So again, our velocity, the distance that we travel, is 185 meters in 4.95 seconds. And the object was not speeding up or slowing down, because again, we're ignoring air resistance here. And this computes out to be 37.4 meters per second. So that's our initial velocity. I'm running out of room, but I'll just continue to move here and I'll rearrange these later. Part C. Now in Part C, we need to know the velocity in the final moments in the y direction. So what is the vertical component of velocity as the ball strikes the ground? So how fast is this moving downward when the object first hits the ground? So that's our final velocity in the y direction. And I think this would be a pretty good formula for us. The velocity final in the y direction is the result of our initial velocity plus acceleration times time. So as we substitute our values, we see that this term is going to disappear, and we have meters per second squared unit that multiplies by a second unit, and that means that our final unit should be meters per second, and the calculated result here is negative 48.6. So that object is moving downward at 48.6 meters per second at impact. I actually solved Part D side by side here so that you can see that the formulas are essentially the same for Part D as well. We need to know the final velocity in the x direction. Well, that's the initial velocity in the x direction plus the acceleration in the x direction times time. And again, the final velocity that we compute is going to be the same as our initial velocity because, again, what we said a minute ago is that there is no acceleration in the horizontal direction. So this 0 meters per second squared times the 4.95 seconds for the object to travel is appropriate here. So we computed the horizontal velocity to be 37.4 meters per second, and so at the end, mathematically speaking, because there was no change in velocity, there was no acceleration, the final velocity happens to be exactly the same. Now, having these two components is really helpful and important for us to answer Part E. What is the magnitude and direction of the ball as it strikes the ground? So as a reminder here, we've got this object that's falling off of or being tossed off the building, and let's try to draw it a little bit more carefully this time. So the horizontal distance of travel was greater than the vertical. So it's falling along this pathway. By the time it strikes the ground, we've now determined that there is a vertical component to this movement of negative 48.6 meters per second, and there's a horizontal component to this motion of 37.4 meters per second. So our horizontal component and our vertical components are imparted on this ball right here at this position. And here again is why we call this the 2D kinematics. We now have direction horizontally and vertically. What we're particularly interested in right now is the result of those two motions, because that will describe this angular direction, if you will. Maybe angular is not the right word, but this diagonal direction. The ball is moving in this diagonal direction. Let's figure out what it is based on our two components. Well, to do that, you may have guessed that a right triangle is necessary. So if I move this vertical component to the right side, we now have a right triangle whose side length here is 37.4 units. Sorry, 37.4 meters per second. And this one is negative 48.6 meters per second. We can calculate this angle measure of the triangle, and we can also calculate the length of that side. Let's go for the length of that side. And I'll call this the resultant vector. So the resultant direction after these two motions are applied to one another is the square root of the sum of these two sides squared. So 37.4 squared plus negative 48.6 squared. And that computes to 61.3 meters per second. So along the diagonal, this thing is moving at 61 meters per second. But if we were to look at the two components, it's diagonally moving at 61, but forward it's only moving 37 meters per second forward and falling at 48 meters per second at that particular moment. The theta value involved can be solved using the inverse of tangent, and this is pretty typical because we have the opposite side length, negative 48.6, divided by the adjacent side length, 37.4, and the computed result from the calculator here is negative 52.4 degrees. And again, that should make sense because we're 52 degrees below horizontal. We only got this result because the opposite side length was indicated as a negative value. So that's why our signs are very important, so that we obtain correct and meaningful results. So I'm going to move these notes off to the side, and then we'll complete this last example. Okay, so in this last example, we have a robot that must throw an object into a container. The robot throws the object with an initial velocity of 78 meters per second. That's pretty fast. At 60 degrees above horizontal, and the object is in free fall for 1.7 seconds before it lands in the container. Now, free fall is an important phrase here. Free fall means that there are no new forces being imparted on the object after it leaves the robot's hands or device, whatever's throwing this ball. So there's no more objects, no wind resistance or air resistance that we have to worry about, but there is going to be acceleration due to gravity. So we would like to know what are the final x and y coordinates of the object before it lands, and we will assume that the origin of this system is located precisely at the point of release. So however this robot is throwing this ball or this object, the point at which it's released, that becomes the origin of this problem. So if we imagine an xy axis, I'll just kind of draw it right here. We're being told that this robot releases the object at 60 degrees with 78 meters per second of velocity. So if it's moving that fast at this angle measure, I'm going to move this down here. I kind of predict the ball will do something like this. And after 1.7 seconds, it might end up here. I don't know if it's going to reach its apex or not, but we'll just kind of draw this diagram and see if it makes sense. But the ball is going to fall in this direction, and we need to find this position. We need to find this coordinate by the time 1.7 seconds has passed. Now again, this is the x and y coordinate after release. The robot could be, down here in this position or something, and the robot's hand might be some measurement above the floor. But as far as this system goes, we're just concerned about when the point of release happens, where does this object land relative to that position? So if it's not immediately clear with the diagram or in the problem, let's try to note our given information. First off, we know that this object is being tracked for 1.7 seconds. The angle of release is 60 degrees, and the acceleration on that object due to gravity is 9.81 meters per second squared. What we need to know is the change in x and the change in y, and we may do this in two calculations, but if we know the change in x, that'll tell us how far this object moves horizontally, and if we know the change in y, that tells us how far that object moves vertically, and those two combined will locate this position of the object after the 1.7 seconds. And so while we may think that we're actually using one of these formulas down below, I don't think that's actually necessary. In fact, these two specifically are really good for uninterrupted, paths of flight, something like this where it follows a curve this way, not one that gets interrupted. So let's go ahead and use our delta x and delta y, motion in single directions, and we'll just combine them as a result here. So I'm going to set up both of those equations here, and we'll complete them simultaneously. Now, it may look like we're missing some information. We don't have initial velocity in either the x or the y direction given to us. And sort of yes and sort of no. We weren't given that outright in the description of the problem, but we can calculate that. Because again, at this moment of release, there is some vertical component and some horizontal component to this motion, and we can actually calculate that by considering the right triangle that's associated with this initial vector. So just like we've done in the past, the horizontal component to this vector, let's label it, the initial velocity in the horizontal direction, is going to be equal to the force in this direction, 78 meters per second. And I suppose we forgot to locate that or supply that in our given information, but that's true. So we've got 78 meters per second times cosine of our angle measure, 60. And then the velocity in our y direction initially is 78 meters per second times sine of 60 degrees. So again, this ball is moving in this direction, 60 degrees above horizontal, but if we were to split that direction into just a horizontal motion and a vertical motion, the combined forces generate the combined motion generates the 78 meters per second, and as it turns out, the horizontal direction, the ball is moving 39 meters per second horizontally, and vertically 67.5 meters per second at the precise instant that this ball is released, when it was traveling 78 meters per second along the diagonal. Now I took some liberties here and included an extra significant figure just to help us with the computations up here. So here I've set up the equations mostly, and again we're doing two of these equations simultaneously. So I wanted to pause for a second though and see if you remember what's happening here. We just computed the initial horizontal velocity to be 39 meters per second, and we know that this is going to this object is moving for 1.7 seconds. But what was the acceleration of x in the acceleration in the horizontal direction in this system? After that ball is released, how much force or acceleration, I should say, is being imparted either forward or backwards? Well, again, hopefully you remember that that's actually 0. There is no horizontal acceleration being experienced by the object because it's in free fall. No outside forces are applying against it. We will treat this value as 0. Now what about in the y direction? Is there 0 acceleration in the y direction? Well, no, not in this case, because we are on Earth and we are experiencing gravity. So we'll say that there is an acceleration, constant acceleration of negative 9.81 meters per second squared. If we weren't on Earth, say in outer space, well, you would know what's happening to that ball, right? It would just continue in the same direction forever and ever. The vertical acceleration is what causes that ball to follow this parabolic path. And that's what makes this problem interesting. As far as solving goes, this component does disappear and the math becomes relatively simple. We end up with a delta x of 66.3 meters. And for delta y, well, again, we've got everything that we need. We'll just enter this into the calculator, and this reports out to be 101 meters. So evidently, if this robot is throwing the object at 78 meters per second, which I said was really fast, in 1.7 seconds, almost 2 seconds later, that ball is 66.3 meters forward and 101 meters above the point of release. So that's pretty incredible. I don't know if that's a realistic scenario or not, but in this particular situation, this is what the math leads us to believe. So lab on Friday is going to be one that involves projectile motion, so we'll be discussing and hopefully testing these formulas for motion in 2 dimensions, as well as our combined or component motion in x and y directions. So hopefully you'll see some more practice with that on Friday, and then again on Monday of next week. That'll be our last time to see each other before our test on the following Friday. If you've got further questions, please let me know. You can send me a message through Schoology or through email. Thanks for watching.